In this presentation, I'll be explaining a three-phase bridge inverter that is operating in 180-degree conduction mode, and we'll be discussing what are the phase voltages, line voltages for a star-connected balanced load. Now continuing a three-phase bridge inverter, that's also called six-step inverter, that is operating in 180-degree conduction mode as such. Now here, this is the circuit topology in which there are three legs are there. For a three-phase inverter, there are three legs, and in each legs there are two switches. It is numbered like this one: T1, then T3, and then T5. This is the odd numbered, and this is a positive group of SCR, and T2, T4, and T6. These are the negative group of SCRs, and across each switch for each SCR, there is a feedback diodes they are connected: D1, D3, D5, D2, D4, and D6. These are called the feedback diodes. And here a DC bus voltage or DC voltage is the V. And to that one, a star connected balanced load is connected, having an impedance in each phase Z. Or this can be considered as even an induction motor. Stator of an induction motor can be considered. So these are the impedances in each phase Z, and it's a balanced load. And this is the, as such, circuit topology as such. And the firing sequence of this one is T1, then after 60 degree T2, then again 60 degree T3, then again 60 degree T4, then again 60 degree T5, and then again 60 degree T6. Then it's continuing. For the firing sequence, T1, T2, T3, T4, T5, T6, then T1, T2, like that. That is the firing sequence. In order to get that firing sequence only, this is numbered like this one. Therefore, T1, T3, T5, this is T2, T4, T6. And in this 180-degree conduction mode, each device or each switching device is conducting for 180-degree duration. That's why it's called 180-degree conduction. And between each two switch, gating of each switch, there are 60 degrees. Therefore, T1 is fired, after 60 degree, T2 is fired. Again, after 60 degree, T3 is fired. Then again, after 60 degree, T4. Then after 60 degree, T5. Again, after 60 degree, T6. Then it's continuing. Therefore, between two firing, there are 60 degrees there, and each device is conducting for 180 degree. That is why it's called 180 degree conduction. Therefore, in 180 degree conduction scheme, each device or switching device conducts for 180 degree. And they are turned on at a regular intervals of 60 degree. So the firing sequence is that T1 after 60 degree T2, again after 60 degree T3, again after 60 degree T4, again after 60 degree T5, after 60 degree T6, then it is again continue as T1. Therefore, that is a sequence of firing of this three-phase bridge inverter. And the output terminals, these are the output terminals. In each leg, the middle point is taken as the output terminal, the phase A, phase B, and phase C. These output terminals A, B, and C of this bridge are connected to a balanced three-phase star-connected load. Therefore, in this case, we are considering a star-connected impedance load, which are balanced one. And star-connected balanced load is being considered here. Is considered as a balanced load is considered. Now continuing the three-phase bridge inverter or six-step inverter, and that's called 180. That is in 180-degree conduction mode, and each device is conducting for 180-degree duration. As already topology I explained, T1, T3, T5, T2, T4, and T6. Across each switching device, there are feedback diodes D1, D3, D5, D2, T4, D6, and there's a balanced star-connected load is there, and DC bus voltage is equal to V. Now coming to this one, here if this is a plot is shown here, that is the top three one are the phase voltages VAN, VBN, and VCNs. And the last three one are the line voltages VAB, VBC, and VCA. We'll be seeing later in each, the derivation of or the plotting of each phase and line voltages. We'll be seeing. And this is the devices that are conducting different duration. It is marked like this one. For example, in here, the T1 is conducting for 180 degree duration in this leg, and the T1, this leg, the other one is the T4. T4 is conducting for 180 degree duration. That is repeating. Similarly, here we can see that one T5. Here T5 is conducting for 180 degree duration and T2 is conducting for again 180-degree duration. Like that, each device is supposed to conduct for 180-degree duration. Now coming to that one, if say for example, if you want to get an output frequency of 50 hertz, therefore this is the phase voltages of a phase A, phase VAN, MVBN and VCN. Now I want to get a frequency of output voltage is equal to say 50 hertz, meaning that the time period is equal to 1 by 50, or that equal to 20 milliseconds. So the time period corresponding to 50 hertz equal to 20 milliseconds. Therefore this is a total time here is equal to, that is equal to 20 milliseconds. Now here that means that each device, that is either T1 or T2 or T3, whatever, that each device has to supposed to conduct 180-degree duration, means each device is supposed to conduct for 10 milliseconds. Therefore, for example, if T1 is fired, that is made to conduct for 10 milliseconds. Again, after that one, again that here we can say that T4 is conducting for 10 milliseconds. Or the firing sequence, we say that T1 is fired after 60 degree. 60 degree corresponds to 3.33 milliseconds for a 50 hertz output. Therefore, after 60 degree or 3.33 milliseconds, T2 is fired. And then again after again 60 degree or 3.33 milliseconds, T3 is fired. Like that one, the firing sequence is T1, T2, T3, T4, T5, T6. And in between that one, the firing, that duration is equal to 60 milliseconds, 60 degrees, or in terms of time corresponding to 50 hertz, it is equal to 3.33 milliseconds. Therefore, if you fire these one in the sequence and each device is supposed to conduct for 10 milliseconds, then output having a frequency, that is fundamental frequency of the output of the inverter, will become 50 hertz. Therefore, these are the phase voltages and these are the line voltages, VAN, VBN, VCN, phase voltages, VAB, that is VAN minus VBN, that is VAB. Like that one can calculate what are the line voltages. We'll be explaining the coming slides all these things. Therefore, these are the voltages, line phase voltages and line voltages, and the firing sequence is T1, T2, T3, T4, T5, T6, again T1. And in between these, each firing 60-degree duration is there. In 50 hertz, it is equal to 3.33 milliseconds. And each device is conducting for 180-degree duration, or for corresponding to 50 hertz, it can be considered as 10 milliseconds. Now continuing the three-phase bridge inverter, 6-step inverter, 180-degree conduction scheme. Already this is the, for a 60-degree, that is 0 to 60 degree, I'm explaining. 0 to 60 degree, if you see that one, T1 and T1, T5, T6 are conducting. T1, of course, T5 and T6 are conducting from 0 to 60 degree. Now, corresponding equivalent circuit, we can see that T1 is closed here, T1 is conducting, then T5 is also closed, T5 is conducting, and T6 is also closed, T6 is conducting. Therefore, if you, this is the circuit, of course, the topology, you can say that when the corresponding thyristors T1, T5 and T6 are switched on, then that is connected to the phases A, B, C, like that one, or the corresponding, this is the supply voltage, DC voltage, and this is the neutral terminal, and the corresponding equivalent circuit of this one corresponding to this connection, this is equal to the DC bus voltage is there. Then we can say that A terminal is connected to plus terminal, and of course the B terminal is here, you can say that B terminal is connected to the negative terminal, that is B is connected to the negative, to the impedance, and C terminal, C is connected to here, that is also connected to the positive terminal. C is connected to the positive terminal, that is the terminal, that is this one is connected to the positive terminal. Therefore here, this is the equivalent circuit corresponding to the case 0 to 60 degree, that is T1, T5, T6. So this is the equivalent circuit, and then we have to calculate what are the phase voltages VAN, VBN and VCN, or this total voltage equal to V. Now if you see that one, if Z and Z equal impedances, and this is a, therefore here the voltage division is that one, here the impedance will be Z by 2, here equal to Z, or here the voltage will become, it is equal to V by 3, and here the voltage equal to 2V by 3. Of course, if you see the voltage of the phase A with respect to neutral, it is equal to V by 3, and the phase voltage of C with respect to neutral, again that is equal to V by 3, or the voltage of B phase with respect to neutral equal to minus 2V by 3. It is equal to minus 2V by 3. That is, it is equal to minus 2, because this is a negative point. Voltage of this one with respect to neutral equal to minus 2V by 3. That is plotted here. That is V by 3 is the voltage here, voltage equal to plus V by 3 VAN, and VCN also equal to plus V by 3, and VBN equal to minus 2V by 3. Therefore, from 0 to 60, these are the phase voltages. And of course, these are the, the line voltages can be calculated by VAB equal to VAN minus VBN. If you calculate VAN minus VBN, you'll be getting it is equal to V will be getting. Similarly, VBC equal to VBN minus VCN. V is equal to minus V will be getting. VBN, VBN minus VCN, or that's equal to, again it is equal to minus V comes, or VCA equal to VCN minus VAN, that is both are equal, that is why it is equal to 0. Therefore, the line voltages are V minus V 0 here, that is plotted here. That is, these three are the line voltages corresponding to 0 to 60 degree. Therefore, in that case, T1, T5, T6 are conducting, and this is the equivalent circuit corresponding to that case, and this is the again reduced circuit. In that one, we'll be calculating what is this voltage VAN and what is VCN and what is the VBN. That is calculated and that is plotted here. Now, one more thing I want to explain, this is called a 6-step inverter. We'll be seeing that one in the output voltage, their transitions are 6 here, there. Not the level as such, transition is there. From here, one state, then again second state, third state, fourth state, fifth state, sixth state. For one cycle, there are 6 changes are happening. That is why it is called 6-step inverter. Of course, the levels will be equal to plus, of course, that the levels will be here. If you face V by 3, 2V by 3, then minus V by 3 or minus 2V by 3. That means the levels will be there. But there are transitions are there, 6 transitions are there. That is why it is called, of course, 6-step inverter as a 3-phase bridge inverter that is operating in 180-degree conduction mode. Therefore, these are the phase voltages and these are the line voltages that is plotted, that is 0 to 60, that is plotted here. Now, next slide we'll be seeing the same working of this one, and the next, that is 60 to 120 degree duration. Now continuing the 3-phase bridge inverter, that is 6-step inverter in 180-degree conduction mode. That now here you will be considering the duration 60 degree to 120 degree. 60 degree to 120 means this duration, 60 degree to 120 degree. In that one, we can see that one, the devices that are conducting, that from this one it is very clear, T1, T2, T6 are conducting. That is 60 to 120. T1, T2, T6 are conducting, or T1 is conducting, that is shorted, and then T6 is conducting, that's also shorted, and T2 is also conducting, that's also shorted. Therefore, you can see that one, always 3 devices will be conducting 180-degree conduction. 2 will be one side, other will be other side. For example, previously 2 was from the positive side and 1 was from the negative side. But in this duration, that is 60 to 120 degree duration, we can see that one, 2 from the negative group, or T6 and T2 are from this one, and from the positive group or positive side, okay, say that positive side, it is equal to one device is conducting. That is T1 is conducting from the positive group and T2 and T6 are conducting the negative group. Now, if you draw the corresponding equivalent circuit up, that can be seen that the supply voltage equal to V, and here only one is connected to the positive group, that is connected. 2 are connected to the negative one, that is 2 are connecting means T6 as well as T2, or here that B phase and C phase, B and C phase are negative. So this is the equivalent circuit corresponding to, this 60 to 120 degree duration. Again, you have to calculate what is the voltage VAN, what is the voltage VBN, and what is the voltage VCN. Again, if you parallel two impedances, parallel impedance means Z and Z, Z by 2 comes. Therefore, here the voltage is it is equal to V by here equal to Z, or that this voltage is equal to magnitude equal to V by 3, and this is equal to 2V by 3. Therefore, the voltage of the phase A with respect to neutral equal to 2V by 3. The voltages of B with respect to neutral equal to, it is equal to here 2V by V by 3 is the, but since it is connected to the negative, minus 2V by 3. Minus V by 3 is the voltage of B with respect to neutral. Therefore, voltage of C with respect to neutral equal to also minus V by 3. These are the phase voltages that is shown in this diagram. It is equal to 2V by 3, then minus V by 3, again minus V by 3, that is VCN, VBN and VAN. And then you will be calculating what are the phase voltage, line voltages, VAB, VAN minus VBN, that is VAN minus VBN, or that is equal to minus plus comes here, that is equal to V. Therefore, here the phase voltage, line voltages, you can see that corresponding line voltage is equal to, that is plotted here, that is VAB, VBC and VCA, that is plotted between the this region 60 to 120 degree duration. That is, this as per this equation, we are calculating what are the line voltages VAB, VBC, and VCA. That is V0, V that are plotted in this line voltages diagram here. V, of course, 0, and here it is equal to minus V. And next slide, we'll be seeing the next one, that is 120-degree duration to the 180-degree duration. Now continuing the three-phase bridge inverter, 6-step inverter, 180-degree conduction mode, and in 120-degree to 180-degree duration. That is 120-degree means this region. In this region, you can see this, what are the devices they are conducting. That is, T1 is conducting, T2 is conducting, and T3 also conducting. T1, T2, T3 they are conducting, and the bridge corresponding equivalent circuit is this one. T1 is conducting, of course here T2 is conducting, and T3 is conducting. Therefore, you can see that one, 2 from the positive side, 1 from the negative side. These are the T1 and T3 are from positive side, and T2 from the negative side. And this is a star connected balanced load. And if you draw the corresponding equivalent circuit here, you can say that the total voltage V, that is here, we can see that 2 are from the positive sides are connected. Therefore, this phase A and phase B, they are connected to the positive terminal, and phase C is connected to the negative terminal. Phase C is connected to the negative terminal. Therefore, the equivalent, you have to calculate what is the voltage division as per the voltage division rule. Here, the total voltage will be divided here 2V by 3, and here V by 3 will be divided. Sorry, here the impedance Z by 2, here V by 3, and here 2V by 3 will be divided. Because the parallel impedance equal to Z, parallel with Z means Z by 2. Therefore, the impedance is less. Therefore, here the voltage is equal to V by 3, and here the voltage is equal to minus 2V by 3, or this voltage with respect to this one equal to minus 2V by 3, and voltage of this one with respect to this equal to plus V by 3. For VAN equal to plus V by 3, and VBN equal to plus V by 3, and VCN equal to minus 2V by 3. Therefore, these are the phase voltages that is plotted here. It is equal to plus V by 3. Again, this is equal to, plus V by 3. And here the third, here also plus V by 3, and this is equal to minus 2V by 3. Therefore, these are the phase voltages. You can calculate the line voltages. VAB equal to VAN minus VBN. Both are equal, that's why equal to 0. Then VBC equal to, we'll be getting voltage V, and VCB equal to again VCN minus VAN, which is equal to minus V. 0V minus V. That is from, okay, 120 to 180. 120 to 180 means this duration. We can see that one. These are the last three one are the line voltages. 0 and plus V and minus V. 0 plus V and minus V. Therefore, these are the phase voltages, and these are the line voltages corresponding to 120-degree to 180-degree duration. These are the devices that are conducting, 2 from the the positive group and 1 from the negative group. Next slide, we'll be seeing the next duration, that is 180-degree duration to 240-degree duration. Now continuing the three-phase bridge inverter in 6-step inverter, 180-degree conduction mode, that is 180-degree to 240-degree duration. And again, that is from this duration, 180 to 240 duration. And the devices that are conducting, you can see that one. From watching this one, you can see that one. T2, T3, T4 are conducting. This duration, T2, T3, T4 are conducting. And the corresponding equivalent circuit equal to T2 is conducting. Therefore, this is shorted. And T4 is conducting. This is also shorted. T2, T4, and 1 from the negative, positive side, that is equal to T3. For T3, T2, and T4 are conducting. Therefore, this is the equivalent circuit, or the reduced circuit will become one phase is connected to the, of course, this is positive. Other two phases are connected to the minus terminal of the source. Therefore, you can say that correspondingly A, here, which is connected, the positive side, B is connected. B is connected to the positive, and A and C are connected. A as well as C are connected to they are connected to the negative terminal of the source. Therefore, this is the reduced equivalent circuit. Again, we have to vote by voltage division. If you parallel to impedance Z by 2 and here Z, then the voltage will be dividing with here equal to V by 3 and here equal to 2V by 3. Therefore, the voltage of this one, B, with respect to neutral equal to plus 2V by 3, and the voltage of A with respect to neutral equal to minus V by 3, C with respect to neutral equal to again minus V by 3. Therefore, these are the phase voltages of, and the corresponding line voltage can be calculated as VAB equal to VAN minus VBN, which is equal to VAN minus VBN equal to minus V, substituting that one. Similarly, VBC equal to VBN minus VCN, which is equal to V, and VCA equal to VCN minus VAN. Both are same. That's why it is equal to 0. Therefore, these are the line voltages and these are the phase voltages corresponding to the uh, conduction region of 180 degree to 240 degree. That is during this region, T2, T3, T4 are conducting, and these are the phase voltages and these are the line voltages. Next slide we'll be seeing the 240 to 300 duration. Now continuing the working of three-phase bridge inverter, that is 6-step inverter in 180 degree conduction mode. Here the firing sequence, firing sequence is T1, T2, T3, T4, T5, T6 in that one, and each device is conducting for 180 degree duration. For 240 to 300 degree duration, we can say that 240 to 300 region, the devices that are conducting, that is equal to T3, T4, T5, T3, T4, T5. Now coming to the corresponding equivalent circuit, T3 is there. This is conducting from the positive side, and then T4 and T5 is also there from the positive side, and T4 is from the negative side. Therefore, the corresponding reduced circuit will be this one. The supply voltage, DC voltage is there, and 2 here we can say that 2 from that is connected to the positive side. That is phase C and phase B, they are connected to the positive side, and phase A is connected to the negative side of the DC bus. Or here again you have to calculate what are the voltages VAN, VBN and VCN. In order to calculate that one, you have to as per the voltage division rule here, these are the two parallel one, Z and Z parallel, Z by 2. Therefore here the voltage division will be, here the voltage will be divided as V by 3, and here the voltage will be 2V by 3. Therefore the voltage of C with respect to N equal to V by 3, and voltage of B with respect to N is also equal to V by 3. But voltage of A with respect to N equal to magnitude equal to 2V by 3, but polarity is minus. Therefore, since it is connected negative, the voltage of A with respect to neutral equal to minus 2V by 3. It is equal to minus 2V by 3. Now, in order to calculate the corresponding line voltages, VAN minus VBN equal to VAB. VAN minus VBN. You can calculate VAN minus VBN, or that is equal to minus V. Similarly, we can calculate what is VBC. That is equal to, both are same. That is why here that is equal to 0. VPN equal to VCA, or VBN minus VCN equal to 0. Similarly, we can say VCA equal to VCN minus VAN, which is equal to magnitude is equal to plus V. Therefore, these are the line voltages corresponding to the region 240 to 300. 240 to 300 region, that is plotted. That is during this region, that is plotted in the phase voltages as well as line voltages. And the next slide we'll be seeing the last session, or that's one, that is 300 to 360 in a one that completes one cycle. Three-phase bridge inverter, that is 180 degree conduction mode. The last section is that in a one cycle, the 300 degree to 360 degree. After that, it's repeating same thing. For 300 degree to 360 degree, what are the device, that is this duration, what are the device they are conducting? Now we can say that T4 is conducting, of course, T5 is conducting, and T6 are conducting. Therefore, always I told in 180 degree conduction, 3 devices will be conducting. One from the either top or bottom, other will be reverse. But the totally 3 devices will be conducting. In this case, T4, T5, T6, T4 and T6, that from the this side negative group, and T5 from the positive group. T5 from the positive group and positive group OCS, and this is equal to negative group. Or the reduced equivalent circuit, this can be reduced as DC bus voltage V, or the battery voltage DC voltage V. And here, since the phase C is connected, only phase C is connected to the plus terminal. That is connected to the plus terminal. Therefore, that is connected. And phase A as well as, of course, B, they are connected to the negative terminal. Then again, you have to, as per the voltage division, here 2 in parallel, Z by 2 comes. Therefore, here the voltage equal to V by 3, and here also equal to 2V by 3. Therefore, voltage of C with respect to neutral equal to plus 2V by 3, and the voltage of A with respect to neutral equal to minus V by 3. Again, voltage of B with respect to neutral equal to minus V by 3. Therefore, again, you can calculate what are the line voltages. VAN minus VBN will be VAB. VAB equal to VAN minus VBN, which is equal to 0. Then VBC, VBN minus VCN, that's equal to, we'll be seeing that's equal to minus V. And VCA equal to VCN minus VAN, that's equal to V. And that is plotted here. That is after the cycle, that is plotted in this one. It is plotted. These values are plotted in the line voltages. And these are the phase voltages. Therefore, that completes one cycle. That is from 0 degree, we There are six, intervals we have discussed: 0 to 60, 60 to 120, 120 to 180, 180 to 240, 240 to 300, and finally 300 to 360 degree. These are the, the top three one are the phase voltages, and other are the line voltages, and this corresponding equivalent circuits also explained. Now consider in a case, same thing, a three-phase bridge inverter in 180-degree conduction mode itself. In that case, the line voltage, and this is the phase voltage as such, phase voltage of phase A, which is equal to V by 3, 2V by 3, minus V by 3, minus V by, V by 3, minus V by 3, minus 2V by 3, again that. Therefore, this is the phase voltage of the AVAN. Now, we are connecting, if you are considering a purely inductive load as such, a star connected purely inductive load, then the corresponding current, if you see that one, these are VA, this is the, the voltage of VAN, that is this voltage is shown here. Similarly, the VBN and VCN will be 120-degree shifted one, VBN and VCN. And the current, if you plot the current through the phase A, in this case, line current is same as the phase current, the case of star connected topology. Therefore, the correct current, line current, which is same as the phase current, can be plotted knowing the phase voltages VAN as well as what the load is. That load we are considering is a purely inductive load. In purely inductive load, that as we know it, it is a voltage across the inductor, that is VL is equal to L DIL by dt, or that indicates that L di equal to VL into dt, or DIL equal to VL by L into dt. Or if you integrate, we will be getting what is the current. IL will come at any time equal to the constant VL by L into T, or Y equal to Mx, that equation, straight line equation, in which the slope equal to the voltage across the inductor divided by the inductance. This is a slope and this is a time variant. Therefore, the current variation is equal to in a straight line fashion, and if the positive voltage across the inductor is positive, it is having a positive slope, and if this VL equal to negative, it will be having a negative slope. Now coming to here, the voltage across the inductor equal to V by 3. That during that period, the current through the inductor or the current through this load as such, that is equal to, that is with a positive slope, the current is increasing linearly. And at this instant, the voltage magnitude has been changing from V by 3 to 2V by 3. Therefore, since VL is increased from V by 3 to 2V by 3, means the slope is increasing with again positive slope, and the slope is increasing. That is why it again this straight line, it is changing, and that is reaching to that one, that is risk point, that is 120-degree duration. And again from here to here, 120 to 180, it is equal to V by 3 plus V by 3 plus V by 3 means again the magnitude, it is having a positive slope only, but the magnitude of VL has been reduced to V by 3. That is why the slope is again as previously case, but it is at a positive slope. It is increasing. Once it is reaching here, you can say that negative voltage is coming across the inductor. Once the voltage across the inductor negative, means that numerator is now negative, or it is equal to the slope is negative. Y equal to Mx means that M will become negative. That is why from here it is having a negative slope, and that slope will be decided by the magnitude of the voltage as well as the inductance value. Therefore, that is this one. And again here the voltage magnitude has been increased to minus 2V by 3. That is why slope is again increasing. Therefore, this is the plot of the current through the inductor, which is same as the line current. Therefore, that is decided by the magnitude of the voltage across the inductor and of course the inductance value. Therefore, that is linearly changing. With a constant voltage across the inductor, the current increases linearly. Therefore, for a purely star connected inductor load here, this is the variation of the line current for a three-phase bridge inverter in 180-degree conduction mode.